algorithm. So next we will move ahead with learn the logistic regression, which is part of the supervised machine learning algorithm. Before that, just a quick recap about the supervised machine learning related problems. So earlier, I don't know how many of you remember it. As part of supervised machine learning, we can solve two types of problem at a high level, right? So what are the two types of problems we can solve with supervised machine learning? How many of you remember it? One is the regression problem. Other one is the classification problem. So the regression problem, how to solve the regression problem? So for that, we have used the linear regression algorithm. Okay, like linear regression algorithm, there are host of algorithms are available to solve the regression problem. For example, you have something called random forest, and you have something else called gradient boosted decision tree, and you have neural network, k nearest neighbor. Likewise, host of algorithms are available to solve the regression problem. We started with linear regression to understand how to solve the regression problem. And now what we will do is we will continue with classification problem. Now let us work on how to solve the classification problem. As part of classification problem, there are three types are there. One is the binary, and other one is multi-class, and the last one is the multi-level classification problem. So what is the binary classification problem? For example, what is binary classification problem? So for example, this is the given data set, and this is your transaction, bank transaction. Okay, and given these information, let's say the transaction number, transaction date and time, amount debited, right? Given these four features, we want the model to predict the class label or the categorical outcome. So whether this transaction is fraudulent or not. Okay, we need to the model has to predict and say yes or no. Okay, so in which category each transaction falls into, whether yes or no. So those transaction falls into the category of yes is called your fraudulent transactions. Okay, so instead of saying yes or no, so we can encode that with the 1 or 0. 1 means the fraudulent transaction. 0, 1 is true, 0 is false. Okay, and in the case of 1, it is true. So the model wants to predict 1. We are very particular about predicting 1. Which all transactions are fraudulent. We are not worrying about the non-fraudulent transactions. We are very particular with the fraudulent transactions, so that the bank can take a swift action in order to trace out why this fraudulent transaction happened, what is the source of the fraudulent transaction. They can take a swift action to fix this issue. Okay, so in this case, to predict the categorical outcome variable is fraudulent as either yes or no, right? So in this case, either yes or no needs to be predicted, or the class label needs to be assigned by the model, right? So the model has to predict and assign the class level, either yes or no. Right? So in this case, this is called your binary class classification problem. You remember I was talking about three types of classification problem: binary, multi-class, multi-level. In this case, this is the binary classification problem. In this case, is fraudulent, yes or no. Okay. So in the case of binary classification problem, right, the classes are mutually exclusive. Yes, yes is different from no, no is different from yes. Okay. So out of these two classes, yes or no, right? So predicting one of two classes only, we do it. Okay. For example, fraudulent or non-fraudulent transaction. In this kind of use case, the binary classification will be done. And also, is this a picture? Is this a cat image or dog image? Right? Yes or no? Okay. In this kind of situation, also we use binary classification problem. Okay, and the binary classification problem, most of the time we solve this one only. Okay, so though we have two more type of classification problems are there, This is the one most frequently many of the machine learning practices, they spend a lot of time in the case of binary classification problem. Okay. The next one is the multi-class classification problem. Okay, let's say in this case, I have a bunch of fruit images. Okay, now we need to classify which all fruit belongs to which category. Okay, so in this bunch of images, in total we have one, two, and three, four, five different fruits in it. So when I show these images to my trained model, it should assign the appropriate class level. So in this case, this is an apple, and this is a pear, and even this is also pear. Though the color is different, but the features are same features, right? So with the that is what pattern. When you train your model, the model not only learns the label, okay, and it learns the pattern also, right? So it assigns this. So in this case, this is an apple and this is your pears, even this is also pears. Okay. In case of avocado, it should assign. So you have you have to group or classify the given images into multiple class. Okay. The next one is multi-label classification problem. The multi-label classification problem, this is the one refers to those classification tasks that have two or more classes. For a single record, we can assign more than one labels, okay, for each record. So in this case, for each record, we assign only one class label. This is apple, this is pear, this is pear. But there are situations, right? There are some scenario you need to assign more than one label for single data, so each record. The classic example is this is the one. So you have a movie, right? So movie. This movie is comedy as well as romance. Okay, you have two labels here. Once we train our model, so given any movie, it should assign two labels. Okay, it should predict. Okay, this is a new movie, and this movie falls under this two categories: comedy come romance movie, something like that. And also predict the presence of multiple known objects in the photo, such as bicycle, person, and person peers, right? Multiple labels are there. So you need to predict multiple objects in the photo, right? So in that kind of situation, also the multi-level classification problem, right, plays an important role. And predict these several tags or label at the time, at the same time, right? So that is what we do it as part of multi-class classification problem. To start with, we will see how we can solve the binary class classification problem using the logistic regression. Before we start with the logistic regression, let's understand there are certain things like probability and odds ratio, because this is one of the building blocks. You should be aware of it. I just go over the basics because obviously understanding probability is central to logistic regression. So we will learn about what odds are, what odds are, and what the odds ratio is. Because again, this is central to understanding logistic regression. Without knowing what is odds, what is probability, there is no point in getting started with the logistic regression related algorithm. Okay, so we'll briefly discuss how to interpret the odds ratio in logistic regression. Okay, so the odds ratio is related to probability and so on. Okay, first we'll start with understand what is probability. So we know very well the probability values ranges between 0 and 1. This is the equation for the probability. Number of favorable outcomes divided by total number of possible outcomes. Number of favorable outcome is there in your numerator. The denominator, you have total number of possible outcomes. Supposing you are tossing a coin, right? So your favorable outcome is head. So what is the outcome that you are expecting? Head, right? So for example, it is 1 getting it. So how many sides are there to a coin? 2 sides, right? Out of the 2 sides, you are expecting 1. So 1 divided by 2 is 0.5. So there is a 0.5 probability that you can get head when you toss a coin. Okay, so the probability value is bounded between 0 and 1. It should not be less than 0, it should not be more than 1, it should be between 0 and 1. The sum of probabilities of all possible outcomes is 1. Okay, this is another rule of thumb, you need to remember it. And this one we will see it later. Okay, next one is odds. What is odds? Odds is something little bit different. The odds of an event, okay, it represents the ratio of the probability of an event occurring over the probability that an event will not occur. This is what calls your odds. So this is what success divided by failure. Okay, the probability of event occurring, the probability of an event not occurring. So for this, this is the equation is used to find out the odds, probability, and if you subtract the probability of success, I say probability of success. If you subtract the probability of success from 1, you will get failure, right? So the failure. So that is the one. See, the sample space. What is sample space? It's something like a universe, the list of all possible outcomes. In this case, what are the possible outcomes? Success or failure? Only the universe you have success or failure. Okay, this is called 1. The value for this one is the sample space is 1. So probability of success and over, if you subtract probability of success from 1, you are left with this one, probability of failure, right? That is what the equation is all about. Okay. Okay, and the next one is okay. What we will do is we will work on this 4 simple problems in order to get a good understanding around, or good get a good grasp of what exactly probability and what exactly odds is all about. So this is the problem. Okay, if the probability of winning is 6/2, what are the odds of losing? What are the odds of losing? Here, total number of possibilities are 12. Okay, out of, right, 6 out of 12 chances, that odds that a person can win, right? If the probability of winning is over to 12, and what are the odds of losing? See, I told you, I gave you the clue. Total number of possibilities. Total possible outcome is 12, right? Out of which 6 are winning. What about the remaining? Very good, Jiva. Super. Okay. Jivanandam, good. You are scaling up well. Okay. See, if somebody says 6/12, right? 6/12 probability of winning. The remaining 6, right? 12. In the 12, out of 12, the probability of winning is 6. The remaining 6, you are losing, right? 6/12. The answer is 6/12, which is what? 6/12 is what? One second. You mentioned about 6, right? 6/12, right? So 1 by 2. One second. Or we can say 6/12. 6/2. Okay, the next question is, if the odds of winning are 13:2, what is the probability of winning? So now they have given the odds. Okay, so in this case, see, in this case, right, if I have to write it in odds of losing, right, 6/6. There is a 6, there are 6/6, right? There is a 6 chances that he can win, 6 chances he can lose. I'll just give you the clue here. The left side of the column is your win, right side of the column is your lose. Now you tell me, if the odds of winning are 13:2, what is the probability of win? Now you need to tell the probability. Probability values bounded between 0 and 1. Now you tell me, what is the probability of winning? What is the total probability here? So the total possible outcome. So look here, this is the winning lose, right? So here the win are 13:12. So 13 is your win, this is your lose. What is the total probability? 15, right? This is success, this is a failure. So 2/15. So if you divide this, whatever you get, that is what the probability of winning. Okay. Probability of winning is 13/15. 13/15, right? Because this is the win, right? 13/15, that is what the probability of winning. And if they give the odds of winning something, right? If they give the odds value, You should be knowing how to convert that into probability. If I ask you, what is the probability of losing? What is the probability of losing in this case? Probability of winning is, see, in the denominator 15, okay? And what is the numerator value? The numerator value, if you put 13, that is what you are winning. What about the, losing? Yes, Gilbert. Gilbert answered correctly. How about others? Jivanandam, okay. No, 13 divided by 15, you will not get 7.5, right? The probability value should be, between 0 and 1. Okay, here in this case, what is the probability of losing? Are you all concentrating here or not? Guys, I gave you the clue, right? The odds of winning are 13 is to 2. That means the total possible outcome is 15. You need to add these two, okay? And how about Aruna? All okay, good. Sumati, very good. And Jivanandam, very good. Okay. So here, probability of losing is 7 is to 1. No, no, no. See, this is the winning, right? This is the winning. This is the losing. Okay. What is the probability of winning? In the denominator, look here. This is the formula. Probability of all possible event. In the case of total number of possible outcomes. Total number of possible outcomes 13 plus 2, right? This is winning means this is losing, obviously. The denominator 15. In the denominator, it should be 15. 13 by 15 is your probability of winning. Okay, 2 over 15 is your probability of losing. Okay, and now the third question is, if the odds of winning are 3 is to 8, what is the probability of losing? Aruna, why don't you tell me this? Mukilan, the same thing. Odds of winning are, in this case, 3 is to 8. That means, the total possible outcome is 11, right? Yeah. No, don't go by the formula. Whatever I gave you the shortcut, right? You go by that. This is your winning. On the left side of the colon is winning and the right side is losing. Okay. And now you tell me what is the probability of losing. Already explained, right? In this one. What is the total possible outcome? The odds of, right? If you convert this into probability, 3 divided by 11, it is the probability of winning, and the probability of losing is 8 over 11, right? That is what the probability of losing. Okay. Out of the 11 possible outcome, there are three chances that you can win, and remaining 8 chances that you can lose. If the probability of losing, now they've given the probability, you need to convert to odds. Okay, and here the total is 8, right? Total possible outcome is 8. What is the remaining 2 is winning. 6 is to, or we can say 2 is to 6, right? 2 is to 6. So, but in this case, what are the odds of winning? Yeah, 2 is to 6. There are 2 is to 6 odds, that a person can win. Okay. You just watch my video and try to understand. If you are not able to understand, you just get back to me. Okay. And okay, now I got answer from everyone. 2 is to, yeah, sorry. Yeah, you are correct, right? Gilbert, you are correct. 2 is to 8, not 2 is to 6. See, out of the 8, right, there is a 6 chances that he is losing. That means the remaining 2 is winning. 2 is to 8, correct. Got it. So if they give you probability, you should know how to convert the some odds, and if they give you odds, you should know how to convert probability. Don't worry. While I explain the equation, how to derive the equation for the linear regression equation, I'll explain you this one. Okay. Okay, so far we have been discussing and building linear regression model in the last session and all. So now we will learn about the logistic regression. And what is logistic regression? Okay, what is logistic regression? See, many business problems and decisions deal with understanding or estimating the probability associated with certain events or behaviors. Okay, for example, a bank, not a bank, the bank in general, right? The loan is one of the most important products of the banking. So what are the other products? Savings account, home loans, family wealth account, car loans, and foreign exchange services, mortgage and right checking account, deposits, credit card. These are the products of the bank. Let's take one of the products, the loan, right? So the loan is one of the most important products of the banking. Okay, the two most critical questions in the lending industry are right before offering the loan to the customer, right? The two critical questions will pop up in the mind of any banking, right? Is this one: how risky is the borrower? Before approving the loan, we wanted to know how risky is the customer, and second thing is, given the borrower's risk, should we approve the loan? So we cannot say all the borrowers are risk free, right? So they don't have any risk at all, right? So already they would have bought the loan, and they would have repaid. There are some customers, they are having already one loan. Now they have applied for the second loan. There is a risk here, okay? But still, they take a look at is other incomes like salary and other incomes, and then they'll decide, okay, can we go ahead and approve the loan? Given the risk, right? Will you be able to repay the loan or not? So these are the two critical questions. Will be asked, right? These are the three critical questions which pops up in all the bank managers' mind, right? Blindly, bank cannot approve or deny the loan for customers, and also with the more number of customers, right? For instance, let's say 1 million customers applied for loan, it is highly unlikely to predict which all customers are going to default within the short span of time. Okay, and that too manually, right? You cannot do it. It will take longer time. And anything, if you do it manually, there could be chances due to oversight. You might tend to, mistakenly approve the loan for a customer who is not at all eligible for loan. So this is where the bank uses machine learning algorithms to predict, which all customers are going to default. Okay, or which are customers are profitable customers. We can say this: which all customers are profitable customers, which means, for those customers we can approve the loan. So using classification algorithms like logistic regression, banks can predict the class level, whether yes or no, whether this customer is fall in the yes category, profitable category, or no, non-profitable category. If it is a fall for profitable category, then close your eyes and approve the loan. Because when you approve the loan, what will happen? So the customer has to pay EMI along with the principal amount along with the interest. The interest is the revenue for the bank. Okay, now let us take a look at this data set. Okay, now let us look at this data set. For example, these four, right? These features are independent variables. Okay, and what the machine learning, what we expect from the machine learning algorithm is whether these customers are profitable customer or not. Look here, this column needs to be predicted by model. My model has to assign the class level. Hey, this guy is yes, which means a profitable customer. No is yes. You can approve the loan for Larry as well as Chris, not people, because my algorithm already we trained with the historical data. Right, since we apply the trained model on these new customers, since my model already learned the various patterns from the huge amount of historical data in the past, right? It can assign the class level, or it can classify which all customers are yes, which all customers are no. Okay, it can predict it. Okay, and now the question is, okay, Larry and Chris are profitable customer. We can but still, the next question that comes to our mind is, so this customer is profitable, but what is the probability that the predicted label is going to be yes? Next question is, can you please quantify? Is there any way if you can quantify, this customer is profit? Is there any way? That is where the probabilities comes into picture. So using logistic regression model, we can not only assign or predict the class level, but also we can assign the probability for each class. Okay. And in this case, or each customer or each example, they say example. So going forward, if I use the term example, which means record. So this first record, second record, third, this is an example, this is an example, this is an example. Okay. Each record is called an example. In the case of machine learning, they use the term example. Okay. So in this case, for each example, along with the classification or the along with predicting the class level, it can also predict the probability. There is a 0.87 probability this customer is going to be profitable. There is a 0.72 probability this customer is going to be profitable. Here, if you see here, there is a 0.23 probability this customer is not going to be profitable. What does it says? So there is no but here, right, something wrong here, right? So ideally, yeah, it's correct, right? So because if you instead of yes or no, if you put 1, 0, 1, right? So if your probability is somewhat closer to 1, that means it is good. But if it is, yeah, 0.23 somewhat closer, correct, right? So that means people, there is a less chances that he is going to be profitable. The 0.23, what it says, there is a less probability that is going to be a profitable customer, right? Hence, is not a profitable customer. Got it? Along with the predicted class label, you can also predict the probability in the case of logistic regression. Okay, logistic regression used when the dependent variable is categorical. When should I use logistic regression? When your dependent variable is categorical. So in this case, the dependent variable profitable. Okay, this is a categorical variable. Okay, this is not a numeric variable. This is not a continuous variable. Can I use linear regression? You cannot use linear regression. Linear regression is used when the dependent variable is continuous. Continuous means quantitative variable, but this is not a quantitative variable. So you might be asking this, and I'm just encoding it as a 1, 0, 1. So can't I say it's a continuous variable or numeric variable? No, because we just did the encoding here, but still, this is a categorical variable. Okay. So this model algorithm is to estimate the probability that an event will occur as a function of other variables. As a function of other variables, then this is the one. Okay, the x1, x2, like a customer, age, gender, income. Okay, and instead of building a predictive model for y directly, like in the case of linear regression model, we predicted the housing price directly. But whereas in the case of log odds, you cannot predict the target variable profitable directly. Okay, you need to use an approach called log odds. That is the difference. Okay, log odds or logit or logistic. Okay, in the case of binary logistic regression, the response variable y is a dichotomous categorical. That means dichotomous is nothing but binary, either yes or no, something like that. Okay, there are three types of there are three types are there in logistic regression. One is the binary, and other one is multinomial logistic regression. So in the case of multinomial, as the name suggests, right? So it will have three or more nominal categories. Okay, for example, you want to predict the type of wine. Okay, it's a red wine or the white one or some other thing. Okay, you have more than two categories are there. So that is what your multinomial logistic regression. And the last one is the ordinal logistic regression. So in the case of the target variable, right, it has ordinal categories such as, the rating 1 to 5, something like that. Okay. So in that case, my model has to predict the ordinal outcome value like 1, 2, 3, something like that. That is what your ordinal logistic regression. But of all these three types, this is the one majority of the time we'll be working on it. Okay. So what are the use cases for logistic regression? What kind of situations can I, in the business situation, can I use logistic regression? Supposing you want to predict the probability an applicant can default on a loan, or predict the churn. What is churn? Customer is leaving my company. Attrition. We say attrition. Cognizant, we could see a lot of attrition, which means the employees are leaving. And we want to predict what is the chances that or probability that my employees can churn, churn. Okay, look here. So this word churn. Churn means leaving the company. Okay, leaving the business or leaving the company. So before even the customer leave the business, if we get to know what is their problem, and if we can address it proactively, which means well ahead, the chances are that the customer will not leave your business. For example, the customer says, "No, I am getting frequent, network, the signal problem." And if they, if they get the same feedback from multiple customers, if they set up, the tower, right, cell phone tower somewhere close by to their area, they can solve their issue so that those customers will not leave your business. But proactively, if you understand what is the customer's problem well ahead, and if you take a swift action, you can retain the customer. How do you know what is there in the customer's mindset? That is where we will be using the classification algorithm, whether the customer is going to leave our business or not, right? So that is what churn, to predict the churn probability. And and also the probability consumers will buy branded or non-branded products. And the next one is the probability of patient successful treatment to a treatment, and what is the probability that customers can develop a heart attack, and will a customer subscribe to an term deposit or not. So these kind of business situations, right, you can use logistic regression. Logistic regression is a classification problem using which we can solve those kind of problems. Okay, so now let us understand the difference between linear regression and logistic regression. The interview, they will ask you this question. Okay, the linear regression used, if your outcome variable or the dependent variable is continuous. If, for example, if your outcome variable is something like weight or height, housing price, stock price, these are all the continuous variable. And what is logistic regression? In the case of logistic regression, the target variable, the dependent variable is categorical. You wanted to predict either yes or no, true or false. Okay. In the case of multinomial logistic regression, you will have more than one class. And in the case of ordinal logistic, you have more than one target outcome. Okay. And apart from this, other differences, in the case of linear regression, the coefficient interpretation is different. And in the case of logistic regression, the coefficient interpretation is different. So in this case, you remember when I use the summary of the model, it gave me the very big detailed summary about the models, right? Model like R squared, adjusted R squared, and what is the method used, OLS method was used. And also we were able to see the other things like count and a lot of other things, right? And but when you see the coefficient for intercept, it already estimated some value. It gives you the estimated value for the intercept and slopes. When you look at, let's say, when you take a specific slope, for example, in the case of size, right? A size is a dependent variable. For that, the slope is estimated something 0.04. That means there is a 1 unit increase in the square feet. There is a there is a 0.04 or cent or dollar increase in my housing price, holding other variables, all other variables constant. This is how we interpret the coefficient, size, and UDS. You remember it, okay? Whereas in the case of logistic regression, it is slightly different. Okay, in this case, what is the probability the customer is going to subscribe? Or the customer has age, right? 25 years. What is the probability that a customer with age 25 is going to subscribe my product, or is going to renewal the plan with us? Okay. And other difference is linear regression uses OLS method, ordinal least squares method, to estimate the parameters. What is parameters? The beta coefficients, the beta 1, beta 2, right? This is your intercept and slope and all, right? So these two parameters, it is also called as a coefficient and parameters. Okay. The ordinal is used to find, estimate the optimal value for this one. And in the case of linear logistic regression, it uses something called MLE. maximum likelihood estimation. Okay, in this case, it uses something called maximum likelihood estimation. So these are the difference between the linear regression and logistic regression. And when it comes to the parameter estimation, right? So to estimate the optimal value for the beta naught and beta 1, it uses the maximum likelihood method. Okay, the maximum likelihood function, right? It determines the parameters, which means the slope and intercept, that are most likely to produce the observed data. Okay, my observed data is something like here, let's say, this is the one I'm talking about, this one. So this is the one. Okay, let's say your actual value is something. You remember in the case of the Excel sheet I've shown you, right? Linear regression, the price, and then next to the price we have something called predicted price. I call this the actual price because this was the one given by my manager, and this is the one predicted by my model, machine learning model. Similarly, when it comes to here, right, the actual label, right? Actually, let's say in this case is profitable. This is 101. Okay, and here for this customer A, okay, let's say Jiva, right? Jiva is a profitable customer 1, right? Let's say Sumati, and she is a profitable customer. And let's say I have someone else, let's say Babu. Okay, he is a non-profitable customer. This is the actual thing. Okay, because based on their past transactions, we have the bank has captured this information. They flagged them. Okay, this guy is profitable because in the past they bought the loan and they repaid it on time. And this guy, no, he did not. Okay, because of given us various factors. Okay, now what is the predicted label, class label, predicted class label? The predicted class label also, the model also predict Geo as profitable customer. It is correct. Okay, and the more, right? So that is what MLE does. The MLE, what it does is it determines the beta naught and beta 1 value. Here also, the intercept and slope is there, like a linear regression model. So the model has to estimate the optimal values for the beta naught and beta 1. So for that, it uses MLE. So what MLE does is, it produces the most likely, produces the output somewhat similar to the original value. The predicted is also 1, and here also 1. If it is 0, then it is good. Like a human, machine learning models can also do misclassification. Sometimes what will happen, instead of assigning the class level as 1, it can assign 0. Okay, so in that case we need to compare this actual and predicted. In case of anything wrong, right, we have something called log loss function. That is the one will help us to measure the model performance. Okay, how accurate the assigned class label, right? The predicted class label. Okay, are they somewhat similar to, are they similar to my this one or not, something like that. Okay, so MLE is basically this function. It estimate the value for the slope and intercept such that, right, most it can most likely to produce the observed data. This is what your observed data, actual. So this value somewhat, the MLE function will try to match with your actual thing somehow, right? So that is what MLE. But still, there are situations, instead of estimating the predicted class label for Sumita, as 1, it can misclassify that. That is the one we need to estimate the model. But the idea of the MLE is that the MLE will try to maximize the predicted class label value somewhat close to your actual value. Okay. Okay. Next, the next thing is, apart from these differences between the linear and logistic regression, and when it comes to the assumptions, are they same? Linear regression makes some assumptions like linearity. And linear regression, does logistic regression also makes the assumptions? Yes. The common assumption is multicollinearity. Even in the case of logistic regression, there should not be any multicollinearity. Okay. And rest of the things are not applicable to logistic regression. The linear relationship, when it comes to logistic regression, it doesn't need a linear relationship between the independent dependent variables, because logistic regression is a non-linear data. Okay, whereas this is a linear one. Linear is something like straight line, but whereas it is not straight line here. Okay, and then the error terms do not follow normal distribution. I will show you why it is not following the normal distribution, and also error terms are not independent and error variance are in heteroscedasticity. You know what is multicollinearity? The correlation between the independent variables are called your this one. These three I will explain you now. Okay, so now the question is, why logistic regression? Why not linear regression to solve this classification problem? So that is what we are going to take a look at it now. Look here in the data set, in the given data set, I have something called age. Age is an independent variable. Okay, and the target variable, right? So you remember the profitable column earlier I shown, right? So there I have shown you yes or no, yes, right? So you assume that in the case of banking data, the dependent variable is default, is default. Okay, here the value will be like 0 1 1 0 0 something like that. Okay, and here the customer name is Jivanandam and Sumati, right? So, and Gilbert and Aruna, right? And we have Vidya, right? And Mukilan. These are the name of the customers, right? In the name column is there, and we have a target value, and age is also there. Each of their ages are there. Okay, and when you plot this one, see the linear regression, the dependent variable was the price, housing price. You remember that was the continuous variable, that was the quantitative variable. But whereas it is a categorical variable, when you plot this data in a chart, it will be something like this. All the zeros will be here, and all the ones because you have only two categories, 0 and 1, right? So all the zeros are plotted here, all the ones are plotted here. If you draw a straight line, if you fit a straight line, what will happen? If you draw a straight line, you have to draw like this, because this line covers all the data, right? All these data, it is somewhat closer to all the data. You see, you have some other things are like this. Okay, something like this. Okay, it is not ending here itself. You have some other observations are there here. The predicted values will lie on your line, straight line, if you use a linear regression to solve the classification problem. So in that case, what problem you pose it here? The first problem is, if you see this actual value and the predicted value for this corresponding actual value is too far. Okay, and here, right here also it is too far, and if you see here, the value here also it is too far. Hence the error terms do not follow normal distribution, the second assumption. Hence it is not following the normal distribution, that the error terms are not independent, it is depending on one another, and also the error variance are heteroscedasticity. If you see here, as the age increases, the error also increases. Look here, 22 23, the age increases, 23, so the error also increases. And when you to look at here 45, the error increases. Heteroscedasticity, the errors do not follow normal distribution, the error terms are not independent, the error variance or heteroscedasticity. Okay, these three linear regression assumptions are violated if you use the linear regression to solve this binary classification problem. Okay, what other issues? There could be chances that it can do a misclassification. For example, this customer is a defaulter. They say you have 24 25-year 26-year-old customer, right? When you fit a straight line, the predicted value for the age 26, right, it comes here, right? So anything, look here, if you draw a line here, right, if you draw a line and here, right, okay, if you draw, let's say this is what your 0.5 probability, right? So, and if you draw a line, and if you see here, right, this observation was wrongly predicted as non-defaulter. Okay, so this is what my 0.5 cutoff. Okay, this is my 0.5 cutoff. Okay, this is my 0.5 cutoff. Okay, and this is 0 to 1, this is the 0.5. Okay, and you have line here, right? The average is here. This is what your intersecting point. And in the case of let's you just think the line is emanating somewhere here, and in that case what will happen is this customer is actually a defaulter, but your predicted value is just below this one, hence we conclude this is a non-defaulter. The chances are that it can do misclassification if you use linear regression algorithm. Okay, then how the logistic regression algorithm works, how this addresses this issue. So in the case of logistic regression, for example, if you draw a line, right, if you draw a line by touching all these things, right, all these value, and if you draw a line, so the predicted value is the line and the actual value is the cross mark. Both the actual and predictor are somewhat close. Both the actual and predictor. So if you draw a line touching all the things, right, the actual and predicted are same. And if you connect these two things, this is something like S curve. Remember that logistic regression, it is an S curve. Okay, linear regression is something like straight line, whereas it is an S curve. Logistic regression. Okay. So now you understood why we need to logist. In the case of logistic, it's an S curve. Okay, and also in the case of logistic regression, the values are supposed to be bounded between 0 and 1. Even this one, right? Ideally, I should have put this one here. You just imagine that, right? So all these things are there here. Okay, and you are here, and all the values are supposed to be bounded between 0 and 1. It should not go anything above 0. 1 is not acceptable. Anything below 0 is not acceptable. But in the case of linear regression, right, it can predict the values above 1 and below 0 also. The values can be predicted anywhere between minus infinity to plus infinity in the case of linear regression. This is also another issue with the linear regression. Okay, that is when we use logistic regression, because the logistic regression is a S curve. Okay, the values are bounded between 0 and 1 in the case of logistic regression. Okay, and the other problem with the logistic regression is something like, let's say a customer, we want to predict whether a customer is going to purchase or not. Okay, we have an independent variable called age. Look at age. Okay, whether this customer is going to buy a product from me or not, we want to predict. Let's say you work for the largest mobile phone retail chain. Okay, they want you to predict whether the customer is going to buy this specific brand or not. Okay, based on the age, you wanted to predict. For the sake of simplicity, I have taken only one independent variable. In this case, age is independent variable. This is my slope and this is my intercept. See, the right side of the equation in the case of logistic regression is also same as linear regression, but only difference in the left side value. Okay, the left side of the equation is different. I will explain a little later. Let's say your model estimated the value for B0 as minus 1.87 intercept. Okay, and the slope is the estimated value like this. And if you multiply this, right, and it should give you the probability. The right side of the equation should give you the probability. The probability value should be between 0 and 1. Right? This result can be interpreted something like that. The probability of purchase equal to 1. 1 means true. 0 means non-true. You will not purchase. We are not worried about the 0. Right? We are very particular 1. What is the probability customer will buy? Right? So for that, this is the equation we got it. Okay, and if you compute this one, right, every additional year of age increases, the probability of purchasing increases by 7.6% in terms of percentage. Okay, that is what we can say. But ideally, it will give us the probability. Now let us plug in the values like this. Okay, this is the equation. This is my intercept. This is my slope. I don't have to compute it manually. These two things, my model estimated. I just plugged in here. Now the question is, let's say my manager is asking these questions. What is the probability that a 32-year-old customer is going to purchase from me? So in the case of age, you are simply put 32 because this you cannot change it. This is estimated by model, computed by model. We don't have any rights to change this one. Okay. Now he has asked this question that so you need to multiply this one, right? And then if you add, subtract this value, in this case, the intercept is negative. What value you will get? That is what your probability. Let's say in this case, 0.562. If you solve this, right? So 72, 762 into 32, and 0.562. Good. Okay. Next is asking another question. What is the probability that a 48-year-old customer is going to purchase from us? This intercept and slope still remain the same. Only thing is the 48 needs to be plugged in here. Okay. So if you solve this, what you will get? You will get 1.778. This is something wrong. It is not falling. This value is not falling between 0 and 1 because the probability value is falling anywhere between 0 and 1. It should not be more than 1. Look here, it should not be more than 1. Okay, this is your 0, this is 1. It should not be above this one. But in this case, it is violating, right? And let's say he's asking another question. What is the probability that a 24-year-old customer is going to purchase from me? And if you plug in 24 years simply, what you will get? What you will get? Can someone tell me? Can you use some calculator and tell me? Minus 0.046, right? In this case, there are two issues. So this is fine. This value is bounded between 0 and 1. But these two are not bounded between 0 and 1. This value is less than 0. This value is above 1. Look here. The probability value should be bounded between 0 and 1. But in our case, the probability of purchase equal to 1 is greater than 1. It is wrong. And in this case, the probability of purchase equal to 1 is less than 0, which is wrong. It is violating the probability rule, right? We need to constrain the probability between 0 and 1. The probability that a 24-year-old customer purchases, right? It must satisfy two things. Either it should be greater than or equal to 0 or less than or equal to 1, right? But it is negative value. The two issues are there. So how we can solve these two issues? That is where the logistic regression equation plays an important role. Okay, to address this more than 1 and less than 0, right? That is to address this issue, they came up with the equation, different equation for logistic regression. So what is the equation? See, look here in this case, right? So probability is equal to exponential of beta naught plus beta 1, and it must be less than 1. So what they do is to solve the first problem. Okay. And okay, tell me one thing. How do you, so in this case, we are getting negative. How do you convert this negative value into positive? Let's solve one, or two. We have two problems. One is probabilities, this is greater than, probability value 1. And this is, less than 0. Yes, one way of doing is you can multiply this. If you square it, minus 0.046 into minus 0.046 is your positive value. You will get it. Or you can take, the absolute value. Absolute, you can take it. What they did, when they developed this equation, instead of squaring the value and or instead of taking the absolute, they have taken an exponential. When you take the exponential on the right side of the equation, the minus negative value will become positive. Okay, they addressed one issue. Okay, when you take the exponential on the right side of the equation, what is my right side of the equation? The b0 plus b1. This is the one. The right side of my equation is b0 plus b1 into h. Don't ask me what is the left side of this equation. That is what we are working on it. Okay, we will derive it now. b0 plus, this is what your right side equation. And if you plug in the value for the intercept and slope and h, and if you multiply, you will get the value. That's what we got. But for a 24-year-old guy, we got minus negative value. But if you take the exponential of this thing, right, it will become positive. Instead of squaring it, use exponential. That is what they did. And okay, by doing so, they address this issue. If the probability value is less than or equal to 0, right, this is the problem we posed. So with this, by taking the exponential, we are able to convert the negative into positive. We address this one issue, and we are still, remaining we are yet to remain, solve the other problem. What is the other problem? The probability value is greater than 1. How do we solve this one? Okay, what they did, they came up with some equation. If you divide any value with the same value by adding a smaller value, you can convert the value between 0 and 1. You take any value. Okay, I will challenge you, take Excel or calculator. For example, 10 divided by 10 plus 1. You see, you are listening, your values P is greater than, look here. In this case, we got how much? 1.778. 1.778, or let's instead of saying 1%, let's say you got 10. Instead of 1.77, you got 10. If you divide the value 10 by the same number by adding a small value to it, let's say in this case 1, right? 10 divided by 10 plus 1, 11. If you do it, it will become, you will get 0 to 1 only. It will get converted as any value between 0 and 1. You take any value in this world, okay? So 1000 divided by 1000 plus 1, it will be bounded between 0 and 1. See, they invented like this, okay? So now, to solve the first problem, you need to take the exponential. Yes, exponential of this one. And, the same value, 10 divided by 10, right? So whatever the value you use the same value in the denominator, and then you add it 1. So now we are able to solve two problems. Okay. So now we got this equation. So what they did, if you take the, they just, simplified this. Instead of e exponential, they, use e to the power. Okay. Instead of e exponential of this one, u to the power, this notation also do the same thing. Okay. And now if you solve this equation, okay, how do you solve this equation? And if you take this denominator on the right side, left side, what will happen? This probability into 1 plus beta naught plus beta 1 into EH, right? If you solve this, right, so P into 1 plus e to the power beta naught plus beta 1, right? Let me do one thing. I need to improve my handwriting. Okay, if you see here, right? So in this case, if you take this on the right side, what will happen? P into 1 plus beta naught plus beta 1 into H. And P into 1 is P plus P beta naught plus P beta 1, right, into H, right? But here the P is common, hence you take the P outside, and you can write it this way also, right? So P, right, so you can do it like this. And if you take the inverse of the log, right, it will get simplified like this. Sorry, if you solve this, right, yeah, P into 1 is P, and P into it is beta naught. And see the same thing, whatever I did it here. Okay, fine. So next one is, okay, I just keep the P only on the left side. And if I, 1 second, let me see what happens here. Okay. And I just keep the P here because I want to find out the probability, right? So what happens, you need to move these things to the right side. In this case, what happens, P is equivalent to e to the power beta naught plus beta 1. And if this one goes on the right side, it will be negative value, right? So if you solve this, if you take this one common, you will get something like this. If you take the inverse of the log on the both side, what you will get is, finally you will get this equation. Okay, natural log of P over 1 minus P is equal to beta naught plus beta 1x. So look here, this is pretty simple, right? In this case, we are just keeping the P on the left side. And if you, since plus value is there here, if you take it to the right side, what will happen? Minus P into e to the power beta naught plus beta naught, right? Beta 1. Okay. And then that is what you have P here. And what you do is e to the power beta naught plus beta 1 plus, sorry, minus P into e to the. So what, instead of, instead of right having the, the lengthier expression on the right side, you can take e to the power beta naught beta 1 as a common value. And if you multiply this, you will get it, right? So e to the power beta naught beta 1 is this one, and minus P into, that is what they simplified this like this. Now they took the 1 minus P to the left side. So when you take the multiplication, right, when if you multiply any value that is multiplied on the right side, if you take it to the left side, it will become your denominator. P over 1 minus P is equal to e to the power beta naught plus beta 1. So now what they did, to remove this e, they took the inverse of the log inverse. They took the log inverse. When you take the log inverse, you need to take the log on the both sides. Okay, natural log of P over 1 minus P. You see, this e will go away since you are taking the natural log on both the side, right? The right side, the e will go away, and you will left with only beta naught plus beta 1x. On the left side, since you have taken the natural log, right, it will remain as it is. This is the equation for logistic regression. This is a simple logistic regression. Obviously, in real-time scenario, we'll be working with multiple logistic regression. Okay, got it? It's very simple. This is how they derived this equation. Okay, in the interview, they might ask you to derive this equation. Any of nowadays, most of us, we are using advanced algorithm, but there are cases they'll ask you like this. Okay, instead of writing this equation, natural log of P over 1 minus P, what we do is, what is P? What we want to predict? True. We are interested in true. One is true, right? Look at this data set. So for these, three independent variables, with the combination of these three, properties, we assign yes here. One is yes, right? We are very particular about what are the chances that, or what is the probability that my customer is going to purchase. We are interested in predicting those customers are willing to buy product. Let's say if I launch a new product in the market, and with this historical data, we want to predict it. What we are interested, we are predicting the customers, those are willing to buy product, if I, my product, right? So in this case, probability of y equal to 1. Instead of simply saying ln, natural log of P over 1 minus P. So natural log of P, probability of y equal to 1, and divided by 1 minus probability of y equal to 1. On the right side, it will remain as it is. Here, 1 is the case of interest, true. The left-hand side is called logit. This is called your logit, logit, or logistic. Okay, since they call it as a logit, because we are taking the natural log, you are taking the log on the left side, hence it is called logit, and it is called as logistic regression. And here the P is the probability of an event, and beta naught is the intercept. Like the right side is similar to your linear regression, but here for to estimate the beta 1, beta 2, and beta, it is using MLE, not OLS, ordinary least squares. Okay, that is only in linear regression. In the case of logistic regression, it uses maximized log estimation. Okay, that is the technique it uses to estimate the optimal value for these two. So now if you simplify this equation further, right, you will get something like 1 divided by 1 plus e to the power z minus z. What is z? Z is nothing but the right side of your equation. You remember, we took the exponentiation of the right side of the equation in order to convert the negative value into positive value, right? So e to the power minus z, we tell. So 1 divided by 1 plus z. So if you can simplify, you will get something. This is what your sigmoid function. This is, remember, this is very, very important. When I talk about neural network, I will be referring to this one, sigmoid function. This is called a sigmoid function. Look here, I mentioned already here. Logistic regression gives an S-shaped curve, unlike a linear regression model. Okay, it gives us the S curve, whereas the linear regression model, it gives us the straight line. But this equation, P divided by, right, this is the same thing. Okay, In shorter form, we call this like this. Okay, this is what your sigmoid function, which is nothing but with this equation we can fit an S curve, because in the case of logistic regression, you are not supposed to fit the straight line. You need to fit the S curve. So in that case, this is the equation is used. This function, right, it can take any real number and map it into value between 0 and 1. The whole idea of this one is you give me whatever number. So in the case of this equation, on the right side of the equation, I plugged in the values. Yeah, here, right? So here we got something like negative value for this, right? Let's say you got something like minus 0.046, something like that. Here 1.77 we got it. You give me whatever the value, okay, 48 or 24 or 1500, whatever the output you get, I don't care, because with my the sigmoid function, I can convert irrespective of the values, between 0 and 1. Okay, full stop. That is what this equation does. That's the reason why you need to use you need to use this equation, because this left side of the equation, it converts or transforms your value to fall anywhere between 0 and 1. Okay. Next one is, we know the probability values are bounded between 0 and 1, but the P over 1 minus P on the left side, we could see that this one, natural log of P over 1 minus P. But in this case, now the question is, why should I take log on the P over 1 minus P? The P over 1 minus P, it takes the values anywhere between 0 to infinity. But if you take a log on this odds ratio, this is your odds ratio. If you take the log on the odds, or odds, we can say odds, log on the odds, okay, it can take values anywhere between minus infinity to plus infinity. Okay, it can take any value between minus infinity to plus infinity, and then it converts that anywhere between 0 and 1. Okay, but log odds ratio will give you the value anywhere between minus infinity to infinity. Okay, and the model, once you fit the model, when you see the summary against each coefficient, okay, you remember in the case of linear regression, along with the size, you found 0.04. This is what the slope value for this size I told you, right? Similarly, in this logistic regression for age, it'll give you something like 6.23, something like that. Okay, this one will be, the coefficient value will be displayed as part of a summary. See, in this case, the slope value is 6.23 log odds ratio. This is not a probability. Once you fit the model in Python or any other statistical software, and if you use a summary to view the coefficient value, the slope values or intercept values in the log odds. Okay, there is a 6.23 log odds ratio. This, the age, the customer with this age, right, will buy so and so thing. Okay. But now the question is, log odds is little bit difficult to interpret. Can I convert the log odds into uh, probability? Yes, it is possible. So in that case, you need to take the exponentiation on this log odds. Okay, you will get the log odds ratio. When you take the exponentiation on this log odds, you will get the odds ratio. So now how do I convert the odds ratio into probability? Odds ratio divided by 1 plus odds ratio, you will get the probability. This is very important. Okay, if you know this one, in the interview they'll ask you, so why should we need to take natural log on the odd ratio, odds? Okay, so the reason is the odds will take the values between 0 to infinity only. When you take the log of your odd ratio, it will take the value anywhere between minus infinity plus infinity. You remember previously we have seen it, right? The negative value we used to get more than 1 also, right? So in that case, what will happen is negative value minus infinity. If you take the log of p over minus p, it can take any value. Okay. And then you will find the slope value, intercept value in terms of log odds. And to convert the log odds, you can take the explanation of that, you can do it. But when you use the predict function, okay, you have something called predict proba function that is available in the logistic regression. Oh, sorry, in Python. Okay, in the sklearn, you have something called predict proba. Okay, and you have something called predict function. Remember, this is pretty simple. Okay, this predict function will give you the class level. It give you the estimated class level, whether this person is going to be profitable. One, this person is so one is true, zero is false. Okay, and just by getting the class level, estimated class level, or by doing the classification not sufficient. Along with that, we need to know the probability. We have some predict underscore probability function is available. With that, you can get the probability for each record. Okay, so but when you use predict probability, it takes care of this automatically. You don't have to do all these steps. But when you look at the coefficient values, the slope for the age is 6.23, and income, you have something income, you have something like 7.25. Okay, so when you see this, it will be log odds ratio. The coefficient values will be in log odds ratio. But when you use predict function, it gives you the output in terms of probability. All right. So this is pretty much about the logistic regression. It is pretty simple, right? Understanding the equation and understanding the odds ratio. And as part of this, right, I explained what is probability, what is odds ratio, and what is the difference between linear regression, logistic regression. Why should we have to use logistic regression? Why we cannot use linear regression algorithm here? Because when you use linear regression algorithm, it violates the three assumptions. Okay, and when you fit the logistic, it can it can do misclassification, that algorithm. Okay, with the help of the logistic regression equation, the natural log of p over 1 minus p, we are able to fit the model or to constrain the predicted value between 0 and 1. And also we have seen how to derive the equation. Fine. Next,